Great, thank you. I can just, yeah.
So, it's my pleasure to introduce Michael Borinsky from Zürich, and who's going to talk about tropical sampling and its application to large loop Feynman integration. So, thank you, Michael.
Yes, thank you for the very kind introduction and for the invitation to speak here today. So I'm going to talk about this tropical sampling and applications to Feynman integrals. This is a much more mathematical topic, but of course it has a connection to physics, namely to the Feynman integrals. And but yeah, for the mathematicians in the audience, it's also about like interesting mathematics that can be applied to physical problems. Yeah, so I'm going to start with some motivation. And the motivation is, like I already said, quantum field theory where the Feynman integrals appear. So these are quantum field theories as we saw them in the talk by Neil already. And for them, these quantum field theories are essentially defined as giving this action, this Lagrangian, as input. And you can think of a quantum field theory as a framework, as a machine where you can just put in this Lagrangian and you get something out of it, some predictions for some measurements or something like this. But for a real quantum field theory practitioner, that's not the end of the story. There's this machinery. It's quite non-trivial, and for like complicated quantum field theories that are formulated in higher dimensions, so in 4 dimensions, for instance, or in 3 dimensions already, there is only one framework or one method to actually crank out proper predictions from this quantum field theory. And this is perturbation theory, this machinery. So how does this work? So we have some observable, which is traditionally expanded in terms of some small parameter called h bar. If you're not interested in physics, it does not really matter what the interpretation of this parameter is. But there are power series that come out of this quantum field theory, and they have some coefficients, an, and h bar is sort of the small parameter in which this is expanded. And there's a tragedy in the context of quantum field theory, namely that it's very hard to compute these numbers, these corrections. And unfortunately, the only sort of way, the only general way to compute these coefficients is to blow up the sum here over these correction coefficients in terms of certain graphs. So we rewrite the sum as the sum of the graphs. So these are the famous Feynman graphs. And for each graph, we have to compute a certain integral. And then an invariant of the graph, so the number of loops, which is the number of independent cycles of the graph, it determines this order in h bar to which this respective integral contributes. And there's a traditional way to write down these integrals, these Feynman integrals, that is written down here, so in terms of d-dimensional integrals over certain spaces. But if you are a mathematician and you don't want to dwell too much on this, then I'm going to present to you a more convenient representation of these integrals later on. There's also a bonus motivation, like exclusively mathematical motivation. That's that if you're interested in an object called tropical geometry or algebraic geometry in general, then this is sort of an easy approach to quantum field theory. So you might be here and have like a general interest in quantum field theory, but sometimes quantum field theory comes with like sort of mathematical caveats. This tropical geometric approach serves sort of as a easy shortcut towards quantum field theory. So that's one motivation. There's a second motivation that came up recently. So in a joint work with Anna-Laura Sattelberger, Bernd Sturmfels, and Simon Thelen earlier this year, we extended these methods to general algebraic integrals that play a role in Bayesian statistics. So in Bayesian statistics, if you want to formulate statistical problems on varieties, you encounter integrals where you have some domain. The domain is the so-called positive part of some variety. And you want to integrate over the quotient of certain polynomials. The polynomials are in sort of the Cox coordinates of these varieties. And the volume form is a standard volume form on these varieties. So these integrals, they, for instance, compute the expectation values of certain experiments on these varieties. And you can formulate many statistical problems and models as such things. So for instance, the Wachs-Press model, or you can also ask simple questions like dice rolling problems and so on. So it's a question in statistics on how to compute these integrals, and also how to sample from the posterior distribution. So we also can think of this differential form as a probability distribution that is given externally, and we want to sample from this probability distribution. So this is what we approached in this work, and this is also something that you can do using these kind of tools. So back to quantum field theory, because I want to focus on these large loop Feynman integral contributions here. So in quantum field theory, recall that we have this perturbative expansion with these coefficients, and it's a very practical problem to compute the lower order coefficients here of these expansions. The reason is that we need these kind of coefficients to interpret the experimental data. And this is actually a kind of a pressing problem, because the physics theory is in a pretty unacceptable situation, that the experimental data from experiments just like CERN is more accurate than the predicted values, sort of in many cases for these standard model computations. So we really need to compute these lower order coefficients to make like more accurate predictions, such that the theoretical predictions are actually more accurate than the experimental data that is being obtained. And I mean, this is also like an economic problem, because of course this data was very expensive. So we really want to keep up as theorists. And so the question is, how can we effectively compute these lower order terms? Like in the context of this conference, there's of course also a related question, which is the sort of resurgence-like question. What's the asymptotic behavior of these coefficients? So if you go to very large n, very large orders in the perturbative expansion, what happens? So there are predictions what's going to happen. So we know that there's going to be some, or we think to know that there's some kind of factorial growth rate. But the quantitative, so the more explicit statement, are kind of conflicting in the literature. People don't know what actually dominates renormalons or instantons in these higher dimensional quantum field theories. So there are special cases where this is known, but this is sort of the perturbation theoretical question around these expansions. What I want to motivate, so actually, because I was just talking about it, so this is also connected, of course, to this very classic study by Bender and Wu, who did actually an empirical analysis of these numbers in quantum mechanics. And there you can really learn a lot just by studying these numbers empirically. And actually this study from '69 and later on gave rise to many fantastic results in quantum mechanics, and you probably all know this. And it would be very desirable to repeat such a study in quantum field theory, in four-dimensional quantum field theory, such that we can actually learn something about non-perturbative phenomena in like the standard model in the same level. But unfortunately, these large coefficients in these expansions, they are not really accessible using present-day technologies, at least yet. And like I said, there's no conclusive prediction for this large order behavior. so this is also like very problematic. So in quantum mechanics, we now also understand it quite well theoretically, but in four-dimensional quantum field theory, cannot really say anything, or we cannot say that much. There's like certain ideas, but they are kind of conflicting. Okay, so there are these two questions, the practical one, the more theoretical one, and the question that I'm going to sort of also trying to foster from this, it's like an overlaying meta question. It's about the computability of these numbers. So the obvious question is like, can we in principle calculate all these numbers? Can we compute them by using a computer and running the computer for a long time? But then the question is like, what's the fastest algorithm to compute these numbers to higher order? And this is, I mean, it seems very theoretical, but it's also a relevant question because the computability question, it encodes the limits of knowledge that can be obtained like from this perturbative approach. Because of course, if we know that the runtime to compute these numbers of an algorithm is too large for like the computation at order 10 or something like this to be finished in any human timescales, then we know that we will never know these numbers beyond this kind of level. So this is the question that motivates this kind of work, and yeah, this is what I'm going to talk about from the physical perspective. All right. So first question: is there an algorithm? And the answer is of course yes. So you just have to pick up your favorite quantum field theory book. So I was giving this talk actually at SLUG, and Michael Peskin, who wrote a very popular quantum field theory book, was in the audience, and he complained that this book is not there. So I'm sorry if your favorite quantum field theory book is not included. But just pick your favorite one. And in principle, if you just take this book and sit down for like a long time, you will be able to compute higher and higher orders of these kind of expansions. So there's an algorithm. But how fast is this algorithm running? So recall that there's this unfortunate situation that we cannot really deal with these coefficients like one by one. We have to sort of use a divide and conquer approach. We have to split everything in these graphs. And so the naive runtime estimate just involves like going over the sum, so taking the number of Feynman graphs that we have to compute and multiplying this runtime with the time it takes to evaluate a single Feynman integral. So the number of graphs that can be estimated quite easily. So it's just some exponential times some gamma function. At least for large n, for large loop order, this is possible. And these numbers, this exponent, this alpha, and the beta shift, they depend on the theory and on the specific observable you are interested in. So this is kind of well understood, and this already gives like a super exponential growth rate for the runtime. And of course, this is like a pretty bad runtime already, but the open question is sort of the time it takes to evaluate a single Feynman integral. And this is what I'm trying to answer, like in this case. So what's the runtime here that we have to multiply this with the runtime to evaluate a single one of these integrals? So the approach that I'm going to take is like the slow but general approach. So we have these kind of integrals. Here's one example. There's also like external data, so this P1, P2, P3 are external momenta, and this is sort of extra information that comes into this problem. And the other data is just this graph, and we can translate this graph into an analytic expression, which is this Feynman integral. And from this analytic expression, I want to sort of count the time, the runtime the computer takes to sort of take this graph's input, go through some intermediate steps, and then end up with a numerical answer. And I would like to do this like in the most general approach. So the strategy is to really start with the slow but general approach and then try to improve it. I'm saying this because there are like there are analytic methods that can evaluate these Feynman graphs, but they all only work in specific cases. So there's no method available that works like for general Feynman integrals. So this is what I call direct evaluation of these kind of things. And yeah, so it's just sort of working with the material that we have. And I don't want to rely on happy accidents that go beyond like these objects being Feynman integrals. Okay, so there's like an algebraic geometric perspective on this that is very helpful. So recall that we have this decomposition into these graphs for these perturbative expansions, and there's a traditional expression for these Feynman integrals. You have to believe me now that we can rewrite these traditional expressions as sort of something that is more algebraic. So this is called the Feynman or the Schwinger trick. But if we apply this trick, then these integrals, they can be transformed into the following form, where we have an integral of a projective space, and we have an actually completely algebraic integral. So these are these integrals that I'm going to be talking about. So they are more accessible for mathematical analysis. So the domain of integration, it's a part of projective space. So we only integrate over the positive part of projective space. So we take all homogeneous coordinates to be positive. And this omega is just the standard volume form on projective space. So nothing special happens there. And this u, g, and fg, these are polynomials now that are invariants of the underlying graph. So I'm not going to give you the formulas for them, but they are like elementary invariants of the graph that you can compute via following some combinatorial game. And they are, of course, homogeneous, such that this is like an honest projective integral. And I also want to mention that there's external data going into the coefficients of this f. So there can also be extra parameters there that I'm not going to talk about in detail. Okay, so the intuition that I would like to convey there is that this is like an algebraic object now, integrals over over projective space, and u and f are homogeneous polynomials. And the intuition comes from the fact that this u and f polynomials, they exhibit very complicated geometries. And these geometries are also very interesting. But these... no, I forgot to define that. I'm sorry. So d and omega g. So d is the space-time dimension, and omega g is another invariant of the graph. So it's just a linear number. It's a number that linear depends on d and on the number of cycles of the graph. So could also write it down, but don't see any chalk. So h1g is the number of loops of the graph, the underlying graph, and e is the number of edges. So that's just an invariant of the graph, and it's exactly. So another explanation is that this omega g forces the whole thing to be of degree 0. So such that it is an honest projective integral. So these integrals, they are hard to evaluate due to this complicated structure. And from a different perspective, this interesting geometry, it makes also these integrals very interesting. So if you try to evaluate them, you will also find that interesting numbers pop up. So there are like many of these zeta values popping up and so on. And these integrals, they also fall into the class of periods as defined by Kontsevich and Zagier. So this is a very interesting generalization of algebraic numbers that you can obtain if you evaluate such integrals. Yes, so the story that so this complicated structure, it even obstructs the numerical integration. So you might think that this is just an integral. We can just put it into the computer and make the computer evaluate it, but the story is not so simple. And I'm briefly going to explain why this is the case. So why is it actually also hard to evaluate these kind of integrals numerically with, or try to do it with black box methods? Because these black box methods, they actually fail. These integrals are too complicated to put into like boilerplate methods. And the reason is that these U and F polynomials, they have like severe roots, so the integrand has severe singularities on the boundary of the integration domain. So they are poles, and we have to control these kind of poles. We have to find local coordinate changes around the poles, so-called blow-ups, such that the integration can be performed by these kind of boilerplate methods, or in general can be performed. Yeah, so I'm going to explain this phenomenon in a very simple example. So there's a very simple integral, and you can compute it. So this is an integral over the unit square in two variables, so x and y. And we integrate over 1 over x plus y. And you can just perform this integral analytically. It's not hard. So the result is 2 log 2. But suppose you didn't know that and you don't want to evaluate this integral analytically. You want to make it using a computer. And also for these two-dimensional problems, we also have like more specific methods available. But suppose we were thinking about like a very high-dimensional problem. So we have to use Monte Carlo to evaluate this integral. So how do we evaluate this via Monte Carlo? We have the unit square. This measure up here, it's like a uniform measure on the square. And we want to evaluate 1 over x plus y. And we just sort of throw darts into the unit square, and we evaluate this integral for each dart square in our unit square. So in formulas, this is written as we average over all these kind of experiments. So we have a 1 over capital N average. So we have capital N many sample points, and for each sample point, we evaluate the integral for the random point. And the random point is just sort of a random point on the unit square. So so if you put this into your computer and sort of take n to be quite large, you will actually get garbage. And the question is, why does this happen? So why can't the computer, or why can't Monte Carlo deal with this problem? And yeah, many of you have probably know this. So the reason is, of course, the error term. So the error term, it scales with the square root of the sample variance over the number of samples. The number of samples we can put like very high, so that's like no problem. But of course, the sample variance in our case, it's infinite, because the original integral is not square integrable. So if we square the integrand, we just get infinity. Then this can be easily checked. So no matter how many sample points we take in this Monte Carlo experiment, we will never find convergence in any way. So naive Monte Carlo integration fails, and we somehow have to do something to get rid of this very severe pole singularity at the origin. And this problem perpetuates extremely in terms of in Feynman integrals. So they are very complicated nested singularities that are nested pole singularities that we have to deal with. And that's the issue why the numerical evaluation of these Feynman integrals is not so trivial. So even this brute force numerical evaluation of the Feynman integrals fails. So I'm going to briefly explain like some traditional solutions to this problem. So all these traditional solutions, they generalize from these nice Feynman integrals with the U and F polynomial. And they replace these with arbitrary polynomials p and q. So this is just an integral over some rational function now. And we can also generalize this to also powers and so on of polynomials, multiple polynomials. But say we just have like completely general polynomials here on this right-hand side. And then one can deal with this via a traditional approach that is called sector decomposition. So this is a systematic way to perform these blow-ups of these algebraic integrals. And it was pioneered by Bino and Heinrich, and later improved by Bogner and Weinzel, who actually realized that this was a very algebraic geometric problem. And there's actually an algorithm by Hironaka that dealt with this problem like in a completely general case. And later also there was also like a simple geometric interpretation by Kaneko and Ueda that I want to mention. But no use of the structure of the Feynman integrals happened on this side. Yeah, so I also want to mention so that these kind of integrals, they also appear like in many other contexts. So they're also appearing in string theory a lot. So they adopt stringy integrals by Akanyameti and Lam. They are also so-called generalized Mellin transformations, and there are a series of very nice works by Passare and people around him in the early 2010s. And we also have an interpretation in terms of toric varieties and toric geometry. So now back to this runtime question. So how long does it take to evaluate such an integral using this traditional blow-up approach? So the rough runtime, so it's a bit tough to estimate these kind of algorithms because they are partially not so explicitly formalized. But an estimate is that the runtime is dependent on the number of monomials in this rational function. And v is this number of monomials. And it scales with v squared times delta to the power of -2. So that's the runtime. And for Feynman integrals, this runtime grows roughly exponentially with the number of edges of the Feynman graph. So we have an exponential runtime with the number of edges. So this now finally brings me to the new results of this work from 2020. So not so quite so new anymore. So the first lesson sort of is from this work was that this numerical integration, it's actually an exercise in tropical geometry. So tropical geometry can be used to perform this to perform this numerical integration and also to formalize this blow-up problem. The second result is that this general approach, it can be accelerated from this v squared times delta to the power of -2 scaling to like a more favorable v squared plus v times delta to the power of -2. So the achievable accuracy from the integration, it partially decouples from the complexity of the integral. And the third point is that at least for Euclidean Feynman integrals, so there's currently ongoing work with 2 students where we extend this to Minkowski Feynman integration, but for Euclidean integration, we can accelerate this exponential growth rate. So here it's like 2 to the power of some constant that is actually quite large times n, the number of edges, to like a more favorable n times 2 to the power of n plus something that is only polynomial in the number of edges. So we have a very nice improvement there. We only need sort of this pre-processing step that is still sort of exponential, but it's sort of on the very tame side of exponential because 2 to the power of n is like a not so large exponent at least. And n to the power of 4 is like a very good polynomial scaling for the large accuracy limit. So there's an in quotes fast algorithm to approximate these kind of Feynman integrals. And to put this into perspective more for the physicists, so these 3-loop computations, they are already quite tough challenges for existing programs. So, and this is also like the relevant field because these 3 loops or order 3 corrections are actually needed for the interpretation of current day experiments. And this is where the current boundaries of the phenomenology is. With this new approach, with the tropical approach, you can go up to 17 loops quite easily with a basic implementation. 17, the limit is then interestingly only coming from the limits in the memory of the computer. So it's like going from CPU time limit to memory limits. And 17 pops up because at this time, so you need a computer, if you implement this in this basic way, that has like 1 terabyte of memory at 17 loops, and I didn't have a computer with more memory than 1 terabyte. Probably you can go higher now. Yeah, so the caveat is that so far only Euclidean and no Minkowski external parameters, but this is an ongoing work in progress, and so far we have very good results, so this is going to be finished soon. Here's an example that is mathematically quite interesting. So this is an 8-loop Feynman integral or Feynman graph. And it's conceptually quite interesting because Francis Brown and Oliver Schnetz in 2010, they proved that this integral is not a multiple zeta value. It's not some evaluation of some polylog or something. They proved that it's something that we don't have a name for. So it's something that we don't really know. And so these kind of interesting numbers sort of are expected to pop up like in higher orders. So the complexity just increases, and the things that we have names for are just sort of appearing like in these very small orders in the perturbative expansion. So with this approach, we can just compute it here to like 7 digits or 6 digits. And yeah, to give you some numbers, so this takes about 10 CPU seconds to get 3 digits for this on a laptop, but it already takes 30 CPU days to get these 6 digits. But of course, you don't make your single computer run for about a month, but you take one computer with 60 CPU cores and run it for half a day. Epsilon is the dimensional regularization parameter. So in this formula, so typically people are interested in this number. So this thing here for this graph ends up being, so in this specific example, it's like epsilon. Right, yeah, so these epsilon expansions are also important, and they can be also computed using this approach. So that's like a first lower bound on the minimal runtime of this algorithm, of this evaluation of the Feynman integrals. And I would conjecture that we can sort of cross out the Euclidean in this statement, and also do this for general Feynman integrals with Minkowski momenta. And also what I want to mention is that improvements are very likely, because this is like a very first approach to do this kind of thing systematically. So yeah, so there are likely like many improvements that we can still accelerate this. So I would also guess, maybe not conjecture, that one can get rid of this annoying exponential runtime here and replace it with a polynomial runtime, actually. But yeah, so this is like more a guess. So we can already use this to like study larger loop regime quantum field theories, for instance, in phi to the 4. And there's a nice study by Gerald Dunn and Max Meinig, who already did this or used like parts of these computations that have been obtained using this algorithm to analyze sort of phi to the 4 theory at quite large loop order, using computations by Eric Panzer, that also, who also used this algorithm to compute higher orders. Okay, so I don't have much time left, but I'm quickly going to explain Okay. How 10 minutes? Okay. Perfect. So I'm going to briefly explain on how this works. So what the key steps are. So the first step is this tropical geometry, and to sort of treat Feynman integrals in this tropicalized way. And to motivate this, we go back to this algebraic geometric perspective on these Feynman integrals with these polynomials. And you recall that this complicated geometry, it sort of obstructs the integration. And there's a very simple solution to this. We just simplify the geometry. And this is sort of exactly the philosophy of tropical geometry. So the motive behind it is always that we take some geometry that is kind of complicated, and we simplify it by sacrificing smoothness for simplicity. So we give up smoothness and in the hope of getting like more simplicity. And this approach, it has various applications and very fruitful applications in algebraic geometry too. So there's a very simple example. So also in the course of this conference, we saw this polynomial equation here a couple of times, the polynomial equation for the circle. And we can say, yeah, the circle is kind of round, and we prefer sort of kinky things. And we also know that it gives rise to complicated numbers like pi that are annoying to deal with because they have infinitely many digits. So we want to tropicalize the circle, and what we do is we just take this polynomial here on this right-hand side, x squared plus y squared, and we take this tropicalization operator on this polynomial. And what it does, it just replaces the plus with a maximum. So instead of x plus y, we just take max of x squared. So x squared plus y squared, we have max of x squared and y squared. And so the circle becomes a square. We squared the circle thanks to this tropicalization operator. And also this has the effect of like making these areas that are surrounded. So here we have pi, and here we have just 4, all rational. And this is a general feature. So we also apply this philosophy to our integrals. This tropical deformation, it rationalizes all our integrals. So they are much easier to deal with on the computer. So computers don't like these kind of numbers, but they like these kind of numbers. So that's the trick. Okay, so just to make this very general, we have some homogeneous polynomial p, and it's written as a sum over some coefficients with some monomials. So here in this multi-index way of writing it, we just tropicalize it by writing first like a superscript trop to the polynomial, and then replacing the sum with the maximum over all the non-zero coefficients. And we just replace the sum over maximum, but we of course only take the maximum over the non-zero coefficients. And also we forget about the explicit value of the coefficients. So the coefficients, they only matter if they are either 0 or not. And this p trop is the tropical approximation of this polynomial p. So it's not quite the tropicalization, but it's closely related to the traditional tropicalization. All right, so we have a nice property of this tropical approximation, namely if this p of x, this original polynomial, if it fulfills a certain technical condition, then the quotient of p over p trop is always bounded from below and above inside our positive projective space. So there are positive constants, C1, C2, that bound this quotient from below and above. So it moves sort of in some window, this quotient. And the proof is pretty obvious. If p of x only has positive coefficients, it's not so obvious. It's harder if p of x has also negative coefficients, but yes. All right, how can we now apply this to the Feynman integrals? We just have this integral with these two polynomials, u and f, and we just replace all the the U and F polynomials with their respective tropicalized version. So this gives I-trop. And because we have those approximation properties, so all these quotients, they are bounded from below and above, this tropicalized integrand, it bounds the original integrand from below and from above with two constants that are not explicit, but we can in principle compute these kind of constants, and we can compute it. So from this it follows that we get like a lower and an upper bound for our Feynman integrals. And this is of course very convenient if you are interested in like large order behavior, that we have like these kind of way to bound things based on these tropicalized polynomials. We can also compute these numbers, like in many cases, at least estimate these constants. So of course bounds are very interesting if you want to prove something. So it's kind of nice. So evaluating these tropicalized integrals is very easy. So you can just put it into the computer, and there's like a well-defined algorithm to evaluate it. So at low order, like up to 20 loops, these integrals can be calculated easily, and all the observables are either numbers or some rational functions. So not so complicated. There's also a related story on like a simplified version of these integrals that is called the Hebb bound, that was studied by Erik Panzer. And this Hebb bound has like interesting relationship to these period integral questions. Then the next step is that if this tropicalized integral, if you can compute it, then this numerical integration of the original integral is just an extra step. So this tropical object is like a very crude approximation, but it bounds everything from below and above. But we can use this approximation to actually also obtain the exact result of the original one by following like a well-defined numerical algorithm that involves Monte Carlo. More recent, there's also like a bonus application of these tropicalized Feynman integrals. So that has been put forward by Akani, Hamed, Hillman, and Misera earlier this year, who used these tropicalized integrals to study IR singularities, so in certain limits of these Feynman integrals. So this is also an interesting new application. But yeah, so in the remaining time, I'm quickly going to talk about this tropical numerical integration, so how this works. So to make the formulas a bit smaller, I'm going to generalize again. So we have, again, P over Q integrals. And the strategy for the overall strategy for the numerical integration is to just treat the original integral as a perturbation around the tropical integral. So we start with this original integral with some quotient of polynomials, P and Q. And then we factorize the integrand in this obvious way. So we just insert a 1. We insert a P trop over Q trop, and we divide it out again immediately. And then we see that this right-hand factor in our integrand is completely bounded. So this factor, due to this approximation property, so recall that the numerator and the denominator, they are always moving only in like a small window between these two constants. So neither the numerator nor the denominator are going to be 0 or infinite. So this part here is bounded, and the remainder of the integrand, it's just a completely tropicalized integrand. So all the complicated stuff has been absorbed in this tropical part of the integral. So in other words, this tropicalization solves the blow-up problem because all the singularities are now described by this tropicalization. And the trick is then to define like a form, sort of tropical form, the mu trop, that incorporates this P trop over Q trop object and identify it as the canonical measure on a certain polytope. So if you know the words, then you will understand, and I say that mu tilde trop is the canonical measure on the common refinement of the normal fans of the Newton polytopes of P and Q. If you don't know these words, then you have to believe me that this mu trop is a canonical measure on a certain polytope. So what this reformulates the original Monte Carlo problem is it rewrites this as throwing darts at a polytope. So we don't throw darts at a square, but we have like a polytope, and a higher dimensional polytope, and we have to throw darts at this polytope to evaluate this integral here numerically. So the sampling from this measure, or sampling from this polytope, it allows for this numerical integration. And fortunately, there's like a reasonably fast algorithm to perform this sampling from this kind of polytope. So for this, you have to triangulate the polytope, and then you can just throw uniform darts at a polytope. That's not so hard. And this gives this second result, this kind of fortunate v squared plus v times delta to the minus 2 scaling of the integral. So so this is the second result, but how much time do I still have? Maybe quickly talk about the very accelerated version. So I'm also mentioned that there's like this further acceleration based on all the structure of the Feynman integral, or not all the structure, but a particular specific structure of the Feynman integrals. And this specific structure that Feynman integrals carry is the structure of generalized permutahedra. So the underlying polytopes for Feynman integrals, they are generalized permutahedra. And for these generalized permutahedra, there's a very fast algorithm to throw darts at these polytopes. So that's the brief synopsis. So the theory of this generalized permutahedra was put forward by Postnikov in 2008. And in the Feynman integral case, it was shown by Schuldger using results of Francis Brown that these polynomials also carry these kind of structures. So here's a picture. So this is one of these normal fans. So you can think about the dart throwing procedure actually like ending up on these like honeycomb structures here in like a higher dimensional space. And each of these cells, these cones in these structures, they are labeled by permutations. So here we have permutations of 3. So that's why it's called generalized permutahedra. So the result is that there's a very fast algorithm to sample from these kind of objects. So there's like a huge shortcut that you can take. And this uses also heavily results from a very nice paper by Agia and Adila, who characterized these generalized permutahedra even more and proved a general universal property on them. So the necessary tools are that there's a facet presentation of these generalized permutahedra. So that's encoded by some function. And the trick for the numerical integration is then to compute from this facet integration like a certain table of partial volumes of these generalized permutahedra that involves these facets. And thanks to this table, one can then write down this quick algorithm to sort of randomly pick points inside these generalized permutahedra polytopes. And just to give you an idea, so this algorithm is then really simple. So there's not only an improvement in the runtime, but there's also an improvement in the inherent complexity of the algorithm, because you just have to follow like, this is like the whole algorithm to sample these kind of points from these generalized permutahedra. You just have to pre-compute some table, and then you just go with your computer through these kind of steps all over and over again to sample these kind of points, and you can evaluate these Feynman integrals very easy. So the traditional computer codes to evaluate these Feynman integrals, they are like huge programs that have to do complicated things. They also have to do these triangulations of polytopes. But in this case, there's really like a very nice shortcut that one can take, and this makes it also much faster. And it's also easy to implement this. So so there's also code for this on my website, but it's not complicated to implement it yourself if you know some programming. Conclusions. So the first conclusion is that the Feynman integrals are surprisingly easy to integrate numerically. And the second conclusion is the more you know about this geometry of the Feynman, of these underlying integrals, so the more information you put in a priori on this tropical geometry, the faster you can make it. So in this generalized permutahedron case, we had like extra input, and we could monetize it and get like an even faster algorithm. And yeah, so relevant for this conference is that this allows to explore like already quite large order regimes in quantum field theory. So one can probably go up to 15 loops perhaps in 4 dimensions. So that's already sort of in the making. But there's also like much left to explore. So there are various improvements to these kind of algorithms. So there's obvious optimizations and less obvious optimizations, and hopefully also surprising new developments. And one particular thing that is very interesting is, of course, to empirically look into these questions on renormalons versus instantons in the large order limit for these, for instance, phi to the 4 or phi to the 3 or other theories. One can also think about extending this notion of the tropicalized quantum field theory, because we can also think about a tropicalized quantum field theory as a certain limit of the original quantum field theory. It's taking the propagator powers to 0 while also taking the dimension to 0 in a well-defined way. So this is also sort of a bit of a pathological, but a limit of usual quantum field theory. And yeah, there's this work in progress on this extension to Minkowski space. All right, thank you.
Thank you. Thank you for this interesting talk. Is there any questions or comments?
So the original integrals for the Feynman graphs, they are over space-time, right? I mean, they are over an unbounded region.
Yes.
So then do you do first, before doing the tropical thing, did you already do a variable transformation so that you reduced it to some finite region? Yes,
that's this projective space. So you can reduce it via this Schwinger trick to a integral of a compact space over this positive part of projective space.
And that compact space is not a nice, so is it not like was it like a sphere? What's the advantage? Like, because you said then it's nice because you have a integral over a polytope.
Yes, eventually.
So before it was not a polytope.
Before it is actually also a polytope. It's a simplex, yes, but it's not the right polytope. You have to pick a different polytope for each Feynman graph.
So then the tropical thing gives you the same polytope, or what?
No.
What's the advantage of exactly from going from one polytope to another?
The advantage is in the original formulation, you have these singularities, these poles, and these poles, they completely obstruct the numerical integration. So you cannot numerically integrate it if you have it in this form due to these poles on the boundary of the integration domain.
So it has nothing to do with the shape of the thing?
No, it has nothing to do with the shape of the domain in the sense, so there's like a duality. So you can shift the complexity into the shape of the domain, or you can, you can interchange complexity of the domain or of the differential form by using variable transformations. Okay. But it always depends.
But then the other part, so then you have this tropical measure, and the factor that is left. Don't you get the same? Is there an intuitive explanation why you don't get the same issues? Like, for example, the whole thing, the whole advantage was to make these coefficients sort of nice and simple, or to make the polynomial nice and simple. But then it's kind of still very complicated, right?
Yes, I mean, the trick is then to use this representation in terms of the polytope to get rid of these singularities. So you find local changes of coordinates that don't have this problem with these singularities.
Okay.
So there's no global change. The reason is that, so it's not a global coordinate change because it's a polytope. So we don't have like global coordinates for this whole polytope. You have to pick like different coordinate charts depending like on which point in this polytope we are. But in this polytope we have local coordinate changes that solve the problem.
So if you have a singularity, it would be something like, you have something like 1 over small, or you have something large in the numerator.
Yes.
So, well, and then, well, if it's a pole, then it's 1 over something very small. But then, even if it's the thing that you then get is finite, you still have something, 2 very small things, no?
I don't quite understand the question, sorry. Maybe we can discuss this later.
Thank you. Are there any further questions or comments?
About Minkowski space, it sounds surprising that it's almost the same speed. Can you comment?
Yeah, so I mean, in Minkowski space there's like one problem, namely that you have to perform an analytic continuation because one has to implement this I epsilon prescription on causality. The moment there's like some way to make sense of this deformation, then it's just the same problem. So what we did was sort of applied like a procedure to perform this analytic continuation, and then one can do it. It's unclear how, I mean, the proof situation is really not so good in this regime because it becomes sort of more of an engineering problem, unfortunately. So it's definitely a conjecture that it's going to be as fast in general, but one can look into it empirically. And I mean, yeah, so the problem there is also that it's hard to actually get reliable data for like larger loop Feynman integrals in Minkowski space because they are just not known. Yeah, so the problem really comes from this analytic continuation, and in principle it's fine, but there's like some engineering issues going in there still.
Thank you for the nice talk. I have a slightly tangential question. You showed us this example by Francis that is not a is not a multiple zeta value.
Yes.
Do people know what type of number is it? Did they try to do some PSLQ over
yeah, it's,
big stuff?
Yes, it's probably some modular form of weight 6, maybe.
Oh, I see. Some L value of modular forms.
Probably you can evaluate it in terms of some L function and so on.
Because there was a conjecture that they were all supposed to be MZV, right? By Francis.
Yeah, so in general you're supposed to these integrals to be MZVs. But in this case, I mean, I mentioned that it's known to something that is not known. So in this context, it's probably expressible still as this special value as some kind of modular form. I mean, this is also a necessity for their proof because they use this to be able to prove that it's not mixed Tate, and that implies that it's not a MZV.
So thank you again to Michael. And I think it's now time for coffee break. Enjoy the coffee.